Okay. Hello, everyone. My name is Kodini Georgiou. I will be doing the presentation today for robotics and AI. I know that not all of you are experienced in engineering, so I'll try to explain them as well, the concepts of engineering and robotics as well as I can. Here is what we're going to cover today. We have the foundation of robotics and mechatronics, programming and control systems, artificial intelligence and machine learning, and advanced robotics and emerging technologies. So I'm going to start from the history. I think this is very important in order to understand how fast robotics and then technology expands, and how fast things are changing. So the first person to introduce robotics, well, the word robot, was Karel Čapek, a Czech writer. The word means forced labor, which is what essentially robots do. They're doing a labor for us. And the second person that's also an author writer is Isaac Asimov in 1942, which he introduced the 3 laws of robotics. The first law is a robot may not injure a human being or through inaction allow a human being to be come to a harm. The second law is a robot must obey the orders given to it by human beings except where such orders will conflict with the first law. So they will do whatever we tell them to do unless they will harm a human being. And the third law is a robot must protect its own existence as long as such protection does not conflict with the first or the second law. So it will have a mind of its own, it will protect itself, but again, it will follow the orders and not bring harm to a human. These obviously were laws made by a writer. It doesn't mean that they are actually applied yet to robots. Here we can see the 3 big waves of robotics. From 1940 to 1970, we have the initial development of industrial robots. The second wave, we have advance in computing and sensors. And third wave, we have the introduction of artificial intelligence and advanced sensors and advanced machine learning. So here is a visual representation of the history of robotics. I'm not going to say a lot of things for this, but I already mentioned the 3 laws. Here we have General Motors uses the world's first industrial robot. This is the Unimate, I don't remember the names, but George Devil and Joseph Engelberg, which is actually considered the father of robotics, introduced this robot that was actually used, the first that was used in industrial setting, and he was doing die casting in New Jersey. Then we have drone, the first unmanned drone that was used, well, one of the first that was used during Vietnam War, if I'm not mistaken. Unmanned means without a pilot, so it went by itself. Here we have the first anthropomorphic robot, so it resembles human form. This is called Wabot 1, and it had actually machine and vision. I mean, when it was the first steps of machine vision. Here we have Puma, that was the first programmable universal machine for assembly, and it was used for surgeries and biopsies. 1986, Honda makes this robot, Asimo, that means advanced step in innovative mobility. So they replicated Wabot robot and wanted to make it more advanced. So to be able, this was not as advanced, so it will wobble, it will fall, and they wanted to make something more advanced. Here we have 1997, the first RoboCup. So you can see mobile robots that play football. Another robot is the robot vacuum. It was introduced in 2002. It's one of the most popular robots. the vacuum robots. Here we have, this is Robotics 2, if I'm not mistaken, and he was the first to be launched into space. Of course, it was by NASA. It had machine learning, AI. It could levitate to microgravity. In 2012, we have the self-driving car. It passed the driving test in America. And we also have, in 2015, Sophia was introduced, one of the most known robots that resembles human features. And actually, something I found out by doing this presentation is that Sophia has a citizenship in I think it's in Saudi Arabia, 2017. It got its citizenship. So that's just something to think about. Okay, first, before I tell you the term of the robot and what it does and what it includes, I want you to tell me what do you think is a robot and what is not. So if you can scan this QR code and you can answer what you think. It has, you can either scan it or use that code on top. If you need the code, I will say it out loud. Your phone. I'm not going to say that there is no right or wrong answer. There is a wrong answer.
Is there a link somewhere so that we can click the link?
So just go to menti.com and use the code that you see on the screen. You can use your mobile phone as well.
Yeah, I have the Zoom meeting is on the phone and it's the text is so small that I can't even see it. So menti.com. Okay.
Okay.
So for those that cannot read the code is 19142030.
Thank you, Mr. George.
19142030. Menti.com.
Doesn't know. Okay, so those of you that didn't manage, you can, I have some more questions, you can log in then. So I wasn't expecting, to be honest, to have so many yes answers. No, actually, a robot is not, sorry, a car is not considered to be a robot. First of all, because it needs a driver. But even if we assume that the car is self-driving car, it's still not really considered a robot. And I will tell you why. Because it does not perform a specific task, and it does not have a manipulation, an actuator, or anything that interacts with something. So it's just driving. It's doing only one task. A robot can do multiple tasks. But it does have robotic characteristics because it's programmable, it can be autonomic, and all of that. Okay, so next one. If for those who don't know who this is from a movie, very nice movie. You can check it out later. I will. Okay. Okay, you can answer now. You have him next door? Oh. I'm not gonna spoil the movie for you, but you should watch it. Okay, so it's obvious, I guess, to everyone that it's a robot. Yes, it is a robot that in the movie, it picks up trash and it cleans the earth. So it has a task and it has hands and it's doing it with its hands. So it's a robot. What about a washing machine? I mean, they are smart, for sure. Okay, again, I didn't expect so many yes answers. It is not considered a robot. It has programmability, adaptability. It does spin, so it does have rotation, but it doesn't do many tasks. It has to perform many tasks and be able to adapt in an environment, so it does not do that. Here we have, I think it's very obvious. Mm-hmm. Okay, I'm glad that there's no more yes in this aspect. It is obvious that it's not a robot, it's programmable, but it does not have an actuator, it doesn't move. Again, this is very obvious, I think. If there's a no answer, I will want the person to explain why not. So be careful. I mean, I did spoil it, but it's very, very obvious. Does someone want to explain to me why it is not considered a robot? Probably not. We have this, a drone. I just have a couple more. Okay, again, it seems that there's a misconception of what a robot is. Drone actually is maybe kind of question because it depends on what the drone does and its capabilities, but mostly it has robotic characteristics. I will explain later why. It is a robot, yes. I think I have two more. Yes, this another one. Promise I'm not gonna make you work later. This is AGV or an AMV, which is an automated guided vehicle or automated mobile vehicle. The difference is one has it follows the line and the other one just moves on its own. Yeah, well, I did say that the vacuum is considered a robot, so therefore it is a robot. And the final one. Okay, well, Siri, Alexa, Amazon Echo, and all of these are called virtual assistants, voice-activated virtual assistants, and they are not considered a robot. They do have robotic characteristics, which is the programmability. They have AI, machine learning, and all those advanced programs and algorithms going on in their microprocessors and such, but they don't do a task. I mean, they do tasks, they help you, they talk to you and so on, but they don't perform or manipulate with the environment. So it is not considered a robot. And here is the term. It's an actuated mechanism programmable in 2 or more axes with a degree of autonomy, moving within its environment to perform intended tasks. This is from ISO. Actuated is to put in a mechanical motion, and autonomy is to perform the tasks with sensing without human intervention. Therefore, now that this term is here, you can understand that since they do not have a degree of autonomy, they don't move around. Alexa, the laptop, the washing machine, they are not considered robots. They do have characteristics, which is programmable and all that. Here is another few terms from NASA. It's the same things. Robots are machines, they do jobs, and they work by themselves. Okay, so characteristics. What characteristics are obvious? They have a mechanical body. They have sensors, they're intelligent, and it has energy to supply all of those things. What is not obvious is how you use them. Are they semi-autonomous? Are they autonomous? How do they work? How does the actuators move from kinematics, forwards, inverse? We're gonna cover that later. Are they fixed? Are they moving? How do they move? Is there a pre-planned path? Do they move according to what they see, or depends on the robots? And of course, do they have constraints or not? And is it only one? Are there multiple? Are they coordinated? And here is what a robot is. It senses, it thinks, and it acts. How does it sense with input, the sensors? How does it think with the control system and the controllers? It has perception and cognition. Perception is what it sees, and cognition is how it understands what it sees, and how does it do the corresponding decision making. And act is the output, which is usually the actuators. So it will either move or move its wheels, move its arms, depending on what robot it is. Okay, about the applications. As you can see here, the industry is ready for the robots. They have invested a lot of money for industrial robots. And this is the industries that are mostly used in. There are 3 major categories: industrial and service robots and educational robots. Industrial mostly refers to non-commercial robots, while service robots refer to commercial use. We have domestic, social, delivery, medical, military, search and rescue, space. We're gonna look at all of those examples. Industrial robots are mostly used for these reasons: welding, material handling, and other applications. They increase efficiency, productivity in the manufacturing. Of course, a human cannot do prolonged tasks as the same as a robot can do. And with the same, it doesn't have the same strength, obviously. Here are some examples. This is articulated robots. They are the most complex in the industry. We have the mobile robots, and of course, the combination of those two. We have the service robots here. They're used to help us clean, help us feed the cat, and so on. Of course, they're used to enhance the quality of life. Here we can see the service robots. We have Aibo, Lovot, and Paro. They're mostly used for to enhance again the quality of life, efficiency, and convenience. They're used mostly as companions. They can interact. They understand human emotions and features, so it can react to it as well. They're mostly used for Paro, especially is used for the elderly, for rehabilitation, when they're not allowed to have animals, but animals is very known to help with rehabilitation, stress, and so on. So they use something similar. I actually saw that robot in person. It moves. It's a seal, and it does move, and its eyes rotate and so on. So it does look very realistic in person. Here we have service robots: Cosmo, Savvy One, Pepper, and Omni Robot. Cosmo is a small robot. It can actuate, it goes up and down, its eyes close, and it makes it look like it has emotion. It's very good for robot enthusiasts, and you can actually program it. It's not like one thing that it does. That is a butler that actually been used in some hotels. Pepper is also a companion. It can understand, has AI, has all of those features. It's made by, I think, made by Aldebaran Robotics, yes. And Omni is a telepresence robot. Of course, it's a service robot because you can have, it's like a fancy Skype or fancy Zoom. You can actually move the robot and interact. So let's say I wasn't here and a robot will do the presentation and then it will come to you and speak to you. It will be the same. It was used a lot during COVID and in universities that had them. And it's becoming very popular now in universities. Other service robots are delivery robots. Sorry. We have some examples here. In other countries, you can see them roaming around. In Cyprus, you cannot. We have medical. Da Vinci is one of the most popular medical robots. It does surgeries. We have Cyberknife, which does full robotic radiotherapy. And the Xenex robot that sprays disinfectant in the rooms. Again, this was going to be very popular during the COVID because the rooms in the hospital were, when it needed to be cleaned, sterilized, all of the rooms and very fast. So this was one way to do it. You have military robots, search and rescue, which all of these have certain mechanical abilities, so they can move around in uneven terrains. And of course, the educational robots that is they're very popular now. It's a new way to learn STEM and explain some technology concepts to students, an easy way to do it. Here in STEM education, that's what they do. Okay, so people think that robots are going to be a problem, that they're going to sell their jobs. But as it mentions here, it is a job displacement. It does not take jobs. So a robot will help a human do a work. It won't take its job. Of course, it introduces more jobs as well because you need someone to take after to program the robots. You need someone to a technician to fix it and so on. So it does create more jobs. It has economic growth, of course, for increasing productivity and efficiency faster than one person does, improve quality of life. And most important for me is that it can perform dangerous tasks so that humans don't have to. So let's say if we go for search and rescue or something like that, you have a bomb threat. Is a person gonna go do it, or are you gonna send a robot that you don't care if it doesn't do the job right? So you're gonna send a robot because it's safer to do it. Or if a room is hazardous, I mean, it has chemicals and stuff like that, you're gonna send a robot to do the tasks. If it's not a smart robot, you can teleoperate it if it's difficult to have full autonomy, but it's still a better way to do it than put humans to do it. Again, this is the concerns, the job displacement, privacy. They think that the data are going to be stolen and so on, especially with artificial intelligence. But there are things that's stopping it from happening. Autonomy decision making. Are the robots ethical? It's a question, because I'm going to ask a different question. Are all people ethical? No, but there is something called roboethics. I'm going to show it a bit later that explains that some things must be taken into consideration when building a robot. So it applies ethical consideration. So it will not, as I said before, it will not harm a human. It will not do all of those things. Security, if they're going to be misused, yes, maybe, but again, depending of who programs it and the way they do it, it's not a concern. And social impact, if it's going to have a problem with human relationships, interactions. Some people are afraid of coming into contact with robots, again, because they're scared of it. But I think we're in now an era that is more acceptable than before. So this is an example. These are movies that have robots in them. For those, well, does anyone know what the main concept is for all of those examples? Has anyone watched any of these movies? Yes, I put them in order of my preference as well. So the basic concept of all of those movies is that robots turn against humans. Most times they also have red eyes for some reason. But how can we ensure that's not going to happen? And here is roboethics. As I said, it's taking consideration scientific, cultural, technical tools that they will be embedded in robotics and promote and encourage their development, help preventing the misuse against humankind. And these are some disciplines that will be taken into consideration. As I said, ethics, philosophy, law, sociology, psychology, computer science, all of those things must be taken into consideration to make a perfectly safe, well, almost perfect, safe robot. So it won't turn against us. But there's always the possibility, I guess, for it to happen. And here I'm going to give you two main types of robots. The mobile robots, which is obvious, is the vehicles that move around the environment, and the robot manipulators looks like this. And it's a fixed base joint robots, and they're very popular in the manufacturing industry. Mobile robots, they can be climbing, walking, flying, swimming, driving, and so on. There are some examples here. There we have, is it Spot from Boston Dynamics? Again, we have Asimo. Oh no, that was Robonaut. We have a drone. As I said, drone is considered a robot, therefore it's in the slide. And we also have actually some that act as, they're more advanced, but the last one is showing a robot that moves like a snake. It's pretty advanced. They're very researching it now. And also we have swimming there. And for the wheeled robots, of course, there are the different type of wheels. And for the flying drones, there are different types. So they're fixed wing, they're the multiple wings, and the hybrid. So of course, depending on the application, you will have to choose what is better for you. If it's high payload, then maybe you will choose the one with more wings, more rotors. And now about the robot manipulator. It has actuators, sensors, and a structural component. The structural component, it has the rigid bodies and the articulations. Rigid bodies are the links, so it's this part here. And the articulations are the joints, which is the part that moves it. I will explain it a bit later. And also it has the end effector, which is the end. So if it's gonna be, it can be a gripper, it can be so many things. It can be actually a paint gun, so it doesn't really, it depends on the application. Here it shows why it's called robotic arm. It's robotic manipulator or robotic arm. It is similar to a human arm. As we have joints, they also have joints, and this is how it looks like. And this is, of course, okay. Show it here. this is the link, and this here is the join. And this part here is the end effector, and this is the base. Okay, so how does it move? It has degrees of freedom. What are degrees of freedom? They are the number of independent variables that define the possible positions or motions. There are two types of degrees of freedom. They're translational and rotational. So it's either moving, rotating, or it's translating. There I have the full degrees of freedom. Actually, I answered the question now, but there you can see forward, backwards, right, left, roll, yaw, and pitch. Roll, yaw, and pitch are also concepts in flying in drones, while left, right, forward, back are for the wheeled robot. So how many degrees of freedom are shown here in the image? How many degrees of freedom in that picture? Yes, there is a wrong answer, which is I don't know, and the right answer, which is 6 degrees of freedom. Because I just actually spoiled the question for you. It's 6 degrees. Not all robots have all 6. As I said, wheeled robots have mostly 2. A drone has 3, and it goes on. Here again, this has showing a 6 degree of freedom robot. That it's not only the arm, but it's also all the human motion. And all corresponds to one thing: the waist, the shoulder, the elbow, the wrist rotating, the wrist bending, and the fingertip. How do they move? As I said, they are rotating and translating. The rotating is the revolute joint, and the prismatic joint is the translation. So it goes forward and backwards. We have other joints. So depending on the application, you have to choose one. The helical has, it's only 1 degree and it's rotating. The cylinder has 2 degrees of freedom. It's rotating and translating, so it goes up. The universal has 2 degrees of rotation, and the spherical 3 degrees of rotation. And also we have different structures. So how do we combine all of those joints? We have anthropomorphic, which is 3 rotational joints, the spherical, 2 rotational, 1 translational. We have SCARA, the selective compliant articulated robot for assembly. It has 2 rotational, 1 translational. The cylindrical robot arm, the rotational translational, and Cartesian, which is all translational. This has very high accuracy, and the spherical is very good with heavy loads. And here we can see 6 degrees of freedom. As I said, it's the highest possible. I mean, it's 6 degrees is the maximum that is used now. You could have 7 degrees of freedom, but that will be redundant since 6 revolute joints create the widest range of motion for a robotic arm. But yeah, you can add a 7th and an 8th, but then you will do a more complex system that has no extra value. If you want, we can have a break or we can continue. Can continue a bit more, okay. So as I mentioned before, robot characteristics have sensors for input, control systems for decision-making, and effectors for output. So I'm gonna explain more about the sensors now. Sensors are devices that enable robots to perceive information. Depending on the application, you get different data. So are you having optical sensors? Do you have touch sensors? And they're different types. They're internal, external, passive, and active. I'm not gonna go into much detail for this, but We're gonna see later some examples of sensors, and it will explain which is which. We also have different input. Is it gonna be a digital sensor that gives 0 and 1? Is it true or false? Or is it gonna be analog sensor that gives a range of values? Here we have some sensors, tactile, motor, and you can see what type they are. EC is the external and PC is the internal, and P is for passive and A is for active. We have switches for the, well, haptic and tactile are pretty much the same thing. Tactile is a part of haptic. Haptic also has kinesthetic, which is a bit different. It's more advanced than touch, but so we also have for speed and identification. So how do we choose which sensors to put in a robot? Okay, it depends on application, but do we want to know the robot's location as well? Or do we want it to just measure, let's say we have an object, is it there, is it not? Do I want to know where is the robotic arm? It will affect the application. So very good sensors for localization are GPS, of course, for outside, laser ranging, radar are LiDAR and LiDAR are the most popular in robotics for localization. And I think I have it here, yes. So these robots, the robotic vacuums, as I mentioned, they can perceive the environment, they can see if there are objects and they are avoiding them. So you need, of course, to know where the robot is in this application. And if I go back, here are some more sensors. These are more for environmental applications. So how do they perceive this information? The sensor gets the data, it extracts some features, so it reduces noise, it does some analysis. And if it has a model, it updates that model in order to use, it uses dynamic model to predict how it will change. I will explain it a bit later even more. And image processing. Why is it needed? If we're using a camera, image processing is very important. Image processing is a subclass of signal processing, specifically for pictures. It has image compression, image enhancement, and image understanding. I will show you image enhancement. This is an example. The robot might not be able to understand what this picture is showing, but if you reduce the noise, it can tell, well, hopefully it can tell that this is a girl. And here I have another example that is for data extraction. First of all, you may have noticed that these pictures are black and white. Why? Because colors are a very wide range. So we use black, white, and gray to have a smaller scale of colors, and it will be easier to compute. And here we're using edge detection. So it detects a local change in image intensity. So by applying different algorithms, doesn't go from there to there. There's so many steps in between. You use different algorithms. You might enhance this, might change the brightness. You can do whatever. There's so many algorithms that you can use to go from there to there. Again, depending on the application, depending on the image you have to figure out what to do. I'm not gonna go into detail. That's too many algorithms to learn. And here we have another example of how it works. You acquire the image, you process it, and then you compare those data to previous data. And that's where artificial intelligence and machine learning start. Here we have optical flow. This is a great example for moving images, or I will say a video. So you can detect a pattern that is in motion. And in robotics, you can use it to navigate and so on. So this is 3D representation and 2D representation. So you can tell that that robot there is moving because those dots are not as close. You can see the rotation. I will give you an easier example, is this one. So this is the mouse. It has optical flow. Mouse has been in use for how many years, Mr. George? At least 50 years. Yes, for the optical mouse. It has a flow sensor at the bottom, and it recognizes that there is a change in motion, and it actually uses 6,000 samples per second to calculate that. So optical flow is very popular for traffic. They use it to view the cars and if the cars are moving. And especially if you want to know if the robot is drifting or so on, you can use optical. Should I continue to the actuators, or do you want to have a break? No? I will move on, and I will make the break a bit later. Okay, so we talked about the sensors. Now we have to talk about the actuators. What actuators am I going to use? Again, depends on the application. But there are two types, linear and rotary. So it's what I'll explain later. It's rotating or translating. That particular one actually does both. We have different power source. So we have pneumatic that work with air. We have hydraulic that work with water. So the water pressure does the actuation, or the pneumatic air does the actuation, or the most popular ones are the electromagnetic one that transform electric energy to mechanical. And here are some examples. The DC motors, brushless, stepper motors, servo motors. Again, if you want to have higher torque, or if you are having high payload, you're not going to use servo, you're going to use one of those motors, DC motors. But the servo motors are very popular in robotics. Here you can see how it works. It gets the signal. You have the power supply or the power amplifier if it's needed, the actuator, and it transmits it to mechanical. As we said, there's 3 types of power supplies. And here I'm going to introduce my favorite part about robotics. It's kinematics and dynamics. You want to know how the robot is going to move. It's not just moving forward or side to side. How does it move? This is a whole chapter of science, and a lot of maths go on for this one, and physics. So it's the study of motion of mechanical points, bodies, and systems without consideration of their associated physical properties and the forces acting on them. So in this case, kinematics, you don't care about the forces. What you care is about the movement. Here is a robot arm, and that is a car, because applies to both types of robots. And here is the forward and the inverse. I'm going to get the manipulator example as it's a bit easier. Forward dynamic kinematics, sorry, is when you know the position of the joints, and you want to find out. So you know where this is. You know the angles of this and this, and you want to calculate the angle of this one. And the inverse, the kinematics is you know where the end effector is, and you want to calculate where this is and where this is gonna be. This is for a 3-degree might not be that hard, but for 6-degree robot is very hard to calculate. You have matrices and all those maths going on to try and figure them out. And you also have differential and inverse differential kinematics, which you know the joint velocities, and you want to find the velocity of the end effector. And inverse, you know the velocity of the end effector, and you want to find out the velocity of the joints. And here we have dynamics, which is with respect to the forces, torques, and accelerations. How does the robot interact? How does it move? Again, you have forward and inverse dynamics. In the forward dynamics, you know the joint trajectories, velocities, and accelerations, and you're trying to figure out you're trying to figure out the joint trajectories from the torques and the forces. And from the inverse, you know the joint motion, and you're trying to figure out the torque and the force and the actuations. I mean, this is what they look like. Of course, I'm not going to go into detail. All of those are translated into matrices, and you have like 5 pages worth of calculations going on to figure out. This is very useful when you're building a robot. If you wanted to perform if you want the end effector to do a specific tasks, it's not just gonna move from one point to another. You have to calculate how it's gonna move. So what is the easiest, let's say the less complex way to go from this point to this point? And have 2 more slides and we're gonna have a break. So those examples, as I showed before, were for wheeled robots or manipulators. Another thing to take into consideration when you're building a robot, I don't know if you're going to build one, but let's say you will, you need, if it's going to be a standing robot, for that example, you need to also take consideration the balance. So you don't want it to fall over. What you want is the center of mass, as you can see there, to be in the support polygon, which is basically the robot's contact points. And of course, it's static balance when it has zero velocity and acceleration. So a robot will, like me, I'm standing right now, have 0 velocity, and my center point, which is here, center of mass, is within, you know, within my 2 legs. So I won't fall over. And we have the dynamic balance, which you're taking consideration that the fact it is walking. So it is a bit more complex. You have to learn about the 0 movement point, which is the sum of the horizontal rotation momentums of the gravitational and dynamic forces is 0. So in order for it to move, that 0 movement point must be again within the support polygon. Okay. So let's say my support polygon is this big. If I do a big step and bend, I will fall. But if I do small steps and I'm still within that polygon, it reduces the risk of me falling over. I could still fall over, but just saying. And the last thing is trajectory and path planning. Path is the order of locus points in the space where a robot will follow, and the trajectory is the path of the path on which timing is important. So I have 3 points. Am I gonna go exactly on those points because it's my path, or will I go in a bit different way just to reduce the time? I think we can take a break now.